For this lesson, we're going to start off with kind of an odd question. This is a question that was apparently given by an elementary school teacher who, as rumor has it, was tired of dealing with their class, and so they just wanted to force these, elementary age children to just sit down and work through this kind of tedious problem, the sum of all the numbers from 1 to 100. And as the story goes, one particularly bright and gifted student gave the answer almost immediately. So I'm starting here because this is very relevant to the first part of this lesson. So how would you go about doing this? Now, we don't want to use a calculator or a spreadsheet or anything modern. And if possible, the student gave this answer without writing anything down, or they wrote down a minimal amount of work. So they certainly didn't add up all these numbers by hand. So what did they do? Now, this unit has been all about patterns and their different forms. And that's true here as well. And in this case, the pattern that we end up being interested in has to do with the fact that pairs of numbers work out to be the same sum. So for example, 1 and 100 add up to 101. 2 and 99 add up to 101. 3 and 98 add up to 101. And so if we look at this from a pairing point of view, there are 100 numbers here, which actually means that there are 50 pairs. And 50 pairs of numbers, each pair of numbers is going to add up to 101. So we end up with 50 times 101 ends up being your answer to this. And so that was a very interesting conclusion. Now, the person who came up with that is Carl Friedrich Gauss. And so they say when he was 10 years old, he was in an arithmetic class. I'll let you read that. You can pause it if you like. I'm not going to read the whole thing if you like. But the rumor is that Gauss took one look at the problem and then came up with the answer right on the spot. Gauss also went on to do very important work in math and physics. So not a surprise that he was a bit of a child prodigy in mathematics. So this idea of looking at basically we start with a sequence of numbers, but we add them together, is leading us into this topic of arithmetic and geometric series. So first of all, a series. A series is simply taking a sequence and adding all of the terms together. So if we have a sequence, which is term 1, term 2, term 3, all the way up to some term n, the series is just taking term 1 and adding term 2, adding term 3, and all of these together give us S sub n, which is the sum of n terms. Okay? So with this entire series, we can actually, for example, the S1 is the sum of the first term. Well, that's just term 1. S2 would be the first plus the second. S3 would be the first 3, and so on. So it's the sum of n terms starting at 1. Or starting at T1. Okay, now what is this value equal to? In the case of an arithmetic series, that means that it came from an arithmetic sequence. You can start with the general term for any term in the sequence, and if you apply some algebra in a somewhat creative way, you can actually come up with two different formulas. Now, one of them is the one that we talked about at the beginning. The idea that each pair of terms is going to have the same sum if you start with the first and the last, and then the second, and then the second to last, and the third to last. They're all going to add up to the same number as the first and the last, just as they did here. So even though 3 and 98 are two particular terms, we don't actually care about 3 and 98 because 3 and 98 add up to the same as the first and the last term. So we just think of this as 50 pairs that all add up to the first and last term. And so that's what I'm saying here. Here's the sum of the first and the last term, the number of terms, and then we divide that by 2. You might wonder, well, what happens if I have an odd number? It will still work out based on the properties of your sequence. So for example, if I had the sequence 1, 3, and 5, well, what do those add up to? I can add the first term and the last term. That's 6. And then I'm going to take that number 6, multiply it by 3, which gives me 18, divide by 2 gives me 9. And then 5 plus 3 plus 1, that gives me 9 as well. So this does work whether the number of terms is even or odd. Another way we can do it is just making use of the values we know, which is the starting value, which is a, so that's our start value, and then d, which is known as the common difference. So we can make use of either of these two formulas. There are going to be circumstances where one is going to be preferable to the other. So let's go ahead and make use of this. Here is an arithmetic series, and I've represented this maybe in a way that's a little bit different. Hopefully it still makes sense to you. We have a starting value of a equals 5. The difference between each of these values, what am I doing each time? I'm adding 4. So that means my common difference is equal to 4. And this part, that's essentially defining the last term. So this is another way of saying that t of n is equal to 4n plus 1. Now notice that this t of n is in a simplified form. The 4 and the d, you can see that is present, but the a is missing. There's no 5 here, and that's because the formula, this formula, has actually been expanded and simplified. So don't get thrown off if something like that happens, because sometimes the simplified form won't match up exactly with your expectations. So this one wants to know what is S of 30? What is the sum of the first 30 terms? So I could do this two different ways. I have two different formulas. The first one, I take the number of terms divided by 2. But keep in mind here, the only difference between the single term and the sum is the number of terms divided by 2. But this has a has become 2a when we sum them. So we could do that S of n is n divided by 2, 2a plus n minus 1 times d, or S of n equals n divided by 2, t1 plus tn. That means that S of 30 is going to be 30 divided by 2. What do I know here? 2a, well, a is 5, so that's 2 times 5, plus n minus 1. Well, in this case, n is 30, so that's 30 minus 1, times the common difference, which is 4. 30 divided by 2 is 15. 2 times 5 is 10 inside the bracket. And then 30 minus 1 is 29 times 4. So the way I normally do that is I say, well, okay, what was 30 times 4 equal to? That's 120. So 29 times 4 must be equal to 4 less than that. So that's equal to 116. And so I end up with 115 multiplied by 126. And I don't think I have a calculator handy, so I'm just going to leave that as a number for now. Now, what about over here? It's still 30 terms, so that's 30 divided by 2. T1, we know that's 5. And Tn, we don't know. So this has to be whatever T30 is. So you might do some rough work where Tn is equal to A plus n minus 1 times d, which is equal to 5 plus 29 times the common difference is 4. You can see we end up in a very similar place that we did before. So 29 times 4 is 116. And then add 5 to that is 121. You might wonder, hold on a second, why was this one 10 and why is this one 5? I'm going to make that clear, I hope, in a moment. So now we continue. S of 30 is 15 in front of the bracket, and then 5 plus, don't forget it was 5 plus T30. But what was T30? 121. And now you can see why this one was 10 plus, because here we had in the formula 2a, whereas in this one we just had to find the single term using a. But there was already an a present, that was T1. So this a plus this a gives me 2a. And that's where that comes in the formula. And so that gives me 15 multiplied by 126. So in this case, I end up with, of course, the same numerical answer. It was probably easier to use the first formula. Both formulas were possible. So in this case, you could use whichever one you're more comfortable with. But I think I could make the argument that going directly to the answer is quicker to go through the first formula. Now, if you're wondering about a formal definition, I'm not going to go into this in gory detail. If we're looking at it in class, I've done a reasonable reproduction here of the proof, but it is a bit tedious. You won't be responsible for this on any of your tests. I'll scroll through this slowly for anybody who wants to take a look at it a little bit more closely in the video, so that way you can pause at different spots and try to piece it together. And let's move on now to the other type of series that we're going to look at in this lesson, which is a geometric series, which is the sum of the terms from a geometric sequence. So here is the formula. And once again, just a reminder, the a, of course, is your starting term or your starting value. And in this case, your r is what's known as the common ratio. And you'll notice that there's a restriction here that r cannot be equal to 1. But that makes perfect sense, because if r were to be equal to 1, it wouldn't be a geometric sequence. It would just be the same number added over and over again. The r value has to be something other than 1 in order to have the sequence itself changing. So just a single formula in this case. It's not the two formulas like we had for the arithmetic series, just a single formula. And so let's go ahead and put that into use. So S of n is equal to a r to the n minus 1 over r minus 1. That's the general formula. And we want to know S of 9 when a is known to be 7, r is known to be 2, so that's going to be 2 to the power n, but n is 9, so that's 2 to the power 9 minus 1, all divided by r minus 1, that's going to be 2 minus 1. And so we end up with 7. Now, 2 to the power 9, I usually remember 2 to the 10 is one that sticks in my mind. 2 to the 10 is 1024. And you can get this very quickly and easily from your calculator. So 2 to the 9 is actually 512 minus 1 divided by 2 minus 1 is just equal to 1. So we didn't even need to write that denominator, but there's no harm in having it. And so we end up with 7 times 511. I still don't have a calculator with me, but this one's not too bad to do because 7 times 500 is 3,500, and 7 times 11 is 77. So we end up with 3,577 is our answer for that one. Okay, so did I answer the whole question there? I did. How about this one? Determine the sum of this series. I just want to keep making sure that this is visible for those of you who are maybe trying to pause the video and work ahead of me. So it's a r to the n minus 1 over r minus 1. And just remember, r cannot be equal to 1. And I think I'm going to need this here, which is that the general term is a times r to the n minus 1, because this one wants to know the sum of this series. But this is a geometric series, because how do I go from 15 to 45? I multiply by 3, I multiply by 3, and so on. So my r value, my common ratio, is equal to 3. My starting value, my a value, is equal to 15. So we know the a value, we know the r value, but we do not know the n value. So n is equal to what? So in order to find that, I'm going to look at this last term, and I'm going to use the formula for a single term in the sequence. So I'm going to say that I'm essentially going to say let Tn be equal to 32805, which means that 32805 must be ar to the n minus 1. 32805 is equal to a, which is 15, and then r to the n minus 1. So that r value was 3 to the n minus 1. And it looks like I'm going to be stuck here. I've got to go get a calculator whether I like it or not. Divided by 15. Actually, I've got a PC open here next to me, so I will use that. And you might be wondering, just how many computers does this guy have around him? I have way too many computers around me. That's the answer to that question. 32805 divided by 15 is 2,187. So that's 2187 is 3 to the n minus 1. And 2187 is a power of 3. So the way we solve this is we want these to be common bases. 3 to the something equals 3 to the n minus 1. And let's see, to do this one in my head, we've got 3 to the 4 is 81, to the 5 is 243, to the 6, to the 7. I believe the answer here is 3 to the power 7. So let me just go ahead and double check that. 3, do I have exponents? Please tell me I have exponents here. There we go. 3 to the power 7 equals 2187. Okay, got that right. A little slower than I'd like, but that's okay. So that means if 3 to the power 7 equals 3 to the n minus 1, then 7 equals n minus 1. N is equal to 8. So now we know that there are 8 terms. You might think we're done by now, but not quite, because now this question mark has changed to a check mark. We know what the n is, which means we can now make use of the fact that S of 8 is equal to a r to the 8 minus 1 over r minus 1. But we know what the a value is. The a value was 15. Our first value was 15, and our r value is 3. So this is going to be 15, 3 to the 8 minus 1 over 3 minus 1. So this works out to be, and once again, going to the calculator. 3 to the exponent 8 is equal to, so this is equal to 15. 3 to the 8 is 6561 minus 1 over 2. And so 6561 minus 1, of course, is just 6560. Multiply that by 15 and divide that whole thing by 2. And we end up with 49,200 is the sum of the first 8 terms in this particular series. And that, you think about it, that makes sense. The last term was 32,000 and something. So the term before that is only going to be a third of its size. So the term before that is going to be about 10,000. That brings us up to 42,000 and so on. And we're adding up smaller and smaller terms all the way down to the first term. So this seems like a pretty reasonable answer. Now, just as I did with the arithmetic series, there is also a derivation for the formula for the geometric series. For any one of these steps, there's no difficulty here algebraically. The difficulty is being the person who recognized that this was a useful thing to do. And that's quite often true in any of these mathematical formulae or shortcuts that you might come across. So again, I'll just do a quick or a slow scroll through the different steps that I have written out. You can find a more comprehensive explanation. I'm sure you could find another video or you could find a document online in a textbook, but at least that way, if you're curious, you can take a look at it. And I believe that takes us to the end of this particular lesson.